This series of lectures, I'm going to talk about the equivalent circuit of a transformer. We have here a model or a diagram of a single-phase transformer. We have a number of turns on the primary, so we've denoted that as MP. We have a number of turns on the secondary, and I've denoted that as N subscript S. There's the primary voltage, and that's understood that has to be an alternating signal, and that comes out as an alternating signal. So that's the primary voltage, the secondary voltage, the primary current, and the secondary current. What we have linking the primary to the secondary is the magnetic core. So this is the magnetic core, which is made of a ferromagnetic material. Which is made of a ferromagnetic material, and that allows the flux produced by the primary coils to link the flux of the secondary coils in order to produce a secondary voltage. One of the things I should have actually said here, what is the electrical or electric equivalent circuit? So we want the electrical equivalent circuit of the transformer. And in fact, what I'd like to do, we'd like to say, rather than using this physical model, we'd like to find what the equivalent electrical model of a transformer is. And in order to understand why we need an equivalent electrical circuit, let's have a look at an example here. So for example, let's assume we had an electric heater, a domestic electric heater. And typically a domestic electric heater might look something like this, and it'll have a grill here and maybe a fan, and inside it has a coil, and then maybe we have something like this. And we would ask the question, why do we need an equivalent model of an electric heater? We're not interested in the shape of the heater. We're not interested in the color of the heater. The only thing we are interested in is how does it behave electrically. So we would say then that the equivalent electrical circuit model of an electric heater is simply a resistor. So we've abstracted everything about the electrical heater into just the equivalent circuit model. And this is useful now because I could actually understand the electrical behavior by, for example, having a single phase AC source, maybe a domestic AC supply of 230 volts AC. And I would connect that to the electric heater, which is modeled here simply as a resistor. And I can then calculate what current flows in this heater and how much heat does it actually generate in terms from a power point of view. So this is actually useful. This is a useful exercise because we've replaced the heater with its electrical equivalent circuit. We've then used that electrical equivalent circuit in an electric circuit. We've understood things about the heater which we needed, and we want to do something similar here. So we want to do away with the physical model or the physical diagram of a transformer, and we want to find what is it equivalent to in terms of an electrical circuit in order to be able to use it in a circuit, run it, and find currents and voltages. And this is actually the essence, and this is the aim of these series of lectures, is to find the equivalent electrical circuit of a single phase transformer in this case.